We appreciate you joining us to go ahead and talk a little bit about your grant here today. We have a lot of folks that are joining us from all over, and I'll go ahead and let them start us off. I know, Bonnie, you wanted to go ahead and offer our first words.
Hi, I'm Bonnie Corcoran. I'm with the Maryland chapter of The Cure Starts Now. My daughter Brenna was treated at Hopkins for DIPG back in 22. We wanted to let you know that on behalf of the DIPG DMG Collaborative and The Cure Starts Now, we're pleased to award you a grant for $100,000 for your work on leveraging epigenetic alterations for therapy of DMG. So
Thank you so
congratulations.
much. Thank you. Wonderful.
Thank you. I'm going to turn it over to Michelle.
I'm Michelle. I'm the president of the Melina Michelle Edenfield Foundation. I am honored to be part of this today to let you know about your awarding of your grant on behalf of the 27 members of our DIPG DMG collaborative. Our collaborative stretches across 5 countries, and we are very proud to show you the support of the amazing work that you are able to do. I'm going to pass it over to Tamara to say a few words.
Hi, my name is Tamara Ikas. I represent the Reflections of Grace Foundation, and so pleased to be with you today and be able to help present this. We have a couple questions. We wanted to better understand how certain compounds, like the one you propose in this, may make DMG cells more visible, and how the application of this research can help additional compounds in the future.
So the DIPG, I know we're supposed to call it DMG now, but I still think of it as DIPG. It's known to be driven by this histone mutation, the K27M mutation, and that's known to change, the epigenome of the cells, to change epigenetic regulation in these cells, which is a mechanism that the cells have that dictates which genes are turned on and which ones are turned off. So this mutation allows the DIPG cells to basically pick and choose any genes to turn on and off. And because it's advantageous to the tumor, they select a set of genes that let them hide from the immune system. They just turn off things that would make them visible to the immune system. So normally, cells that are unhealthy or that are infected or that have foreign things going on kind of hold up a flag to the immune system that says, there's something wrong and they should be attacked. And cancer cells find a way to turn that off. So they effectively hide from the immune system, making them, essentially invisible, and they can grow and avoid, the body's defenses. And so the strategy here is that we basically reactivate immune signaling in the DIPG cells. So we convert them from what's called immune cold to immune hot. So they had turned down these kind of immune surface molecules. They hid kind of some of the potential targets or antigens that are inside the cells. And they're basically trying to escape and trying to hide. And we exploit kind of the same epigenetic mechanism that the cells used to reverse that and to turn those genes on. So the specific, drugs that are discussed in the proposal, I think, have a lot of promise and are already, in clinical use in other disorders, but there can be other, lots of other epigenetic strategies to basically just change what genes the DIPG cells can express. So the idea is, whatever they're trying to hide, kind of whatever they're trying to turn off, we will kind of unmask that, switch it on, and at the same time, kind of stimulate the immune system to find these cells and fight them. And there are already lots of great strategies for using the immune system to fight cancer in general. There's, the immune checkpoint inhibitors, there are CAR T cells. They just work, pretty inconsistently. And a lot of cancers in DIPG specifically have found a way to kind of avoid immune destruction and to effectively escape from the immune system. So this is kind of a complementary strategy to immunotherapy, right? Activate immune signaling, activate immune visibility in these cells, and then couple that with the application of immunotherapy, which would allow us to actually destroy DIPG cells. And another, another, I guess, advance here in this particular proposal is a lot of the models of DIPG that we, all the scientists kind of across the field have used. A lot of these models don't involve the immune system at all. They use immunodeficient mice. They put human tumors in mice without an immune system. And everything we do is in the absence of immune signaling, which is not what happens in actual patients, right? So here we're proposing to study these new drugs and these new immunotherapy strategies in an intact, competent immune system using Dr. Becker's mouse models.